Despite being predicted by theoretical physicists nearly a century ago and created in laboratories, since antimatter remains one of the universe's greatest enigmas, why is there so little of it? What makes it so dangerous yet so valuable? In this episode, we'll explore the origins of antimatter, its incredible properties, and cutting-edge research at facilities like CERN, where scientists are pushing the boundaries of our understanding. Get ready to embark on a journey into the unknown, where science fiction meets reality, and the mysteries of antimatter await. Let's dive in. The rarity and danger of antimatter. Antimatter is incredibly rare in the universe, even though theories say it should be as common as regular matter. When antimatter meets regular matter, they annihilate each other, releasing vast amounts of energy. Just a small amount could cause massive explosions. Handling antimatter is super tricky because it can't touch anything without exploding. Scientists are trying to figure out why there's so little antimatter and how to use it safely for considerable scientific advancements. What is antimatter? So what is antimatter? It would look just like regular matter if we had enough of it. The idea of antimatter was predicted before it was even discovered. 1928, English physicist Paul Dirac worked on an equation to describe electron behavior. This equation had two solutions, one describing the electron and the other describing a particle identical to the electron, but with a positive charge. This particle, later discovered and named the positron, was the first known antimatter particle. Discovery and creation of antimatter. In 1932, physicist Carl Anderson's discovery of the positron in a cloud chamber provided the first concrete evidence of antimatter, revealing that every particle of matter has a corresponding antiparticle with an opposite charge. However, creating antimatter has proven a formidable challenge due to its annihilation property. It instantly disappears upon contact with regular matter. It wasn't until 1995 that scientists successfully produced the first antihydrogen atom. Despite these breakthroughs, the intricacies of handling and studying antimatter persist, underscoring the complexity and importance of ongoing research. Antimatter at CERN. At CERN, the European Organization for Nuclear Research, scientists are delving into the mysteries of antimatter using some of the world's most advanced technology. One of the key facilities for this research is the antiproton decelerator, AD, where antiprotons are slowed down to allow for detailed study. The AD is nestled within a concrete tunnel, shielded to ensure safety. Antimatter particles are carefully directed and manipulated using powerful magnets, precisely controlling their paths. However, this process demands enormous amounts of energy, contributing to the astronomical production cost of antimatter. Despite these challenges, AD is vital in advancing our understanding of antimatter and its potential applications. The cost and value of antimatter. Antimatter, while incredibly rare, holds an unparalleled value in scientific exploration. Its production costs are astronomical, with estimates suggesting trillions of dollars for just 1 gram. Despite this, the potential applications of antimatter are vast, ranging from advanced medical treatments to revolutionary propulsion systems for space travel. However, realizing these possibilities requires overcoming significant technical challenges. Institutions like CERN are at the forefront of antimatter research, driven by the promise of unlocking its secrets and harnessing its power for the benefit of humanity. The big question: why so little antimatter? According to theories, the Big Bang should have produced equal amounts of both, yet we observe a universe overwhelmingly dominated by regular matter. This glaring asymmetry presents one of the most profound mysteries in modern physics. Scientists are actively exploring various hypotheses to unravel this enigma, conducting experiments and theoretical investigations to understand the processes that led to the imbalance between matter and antimatter. Current research and experiments. Current research and experiments in antimatter focus on refining production and trapping methods for particles like antiprotons and positrons. Scientists utilize advanced particle accelerators, such as those at CERN, for these studies. Additionally, researchers investigate how antimatter behaves under different conditions to uncover any disparities with regular matter. Practical applications, from medical diagnostics to space propulsion, are also being explored. These efforts aim to deepen our understanding of antimatter and its potential applications. In the future, antimatter research is poised to undergo significant advancements across multiple fronts. Scientists anticipate refining production and manipulation techniques, potentially leading to more cost-effective methods for studying antimatter. This could involve the development of innovative particle accelerators and trapping technologies. Furthermore, there's growing interest in exploring practical applications of antimatter beyond fundamental research, spanning fields such as medicine and space exploration.